Hello and welcome back. This is our next example of optimization, and in this problem we want to find the largest rectangle that we can inscribe in the parabola y equals 9 minus x squared above the y-axis. And the key word here is inscribed. That means that it fits under or within the parabola, and the endpoints of the rectangle are going to be sitting on the actual curve itself. So the picture to have in mind here is going to be your standard parabola, which opens downward and has a y-intercept of 9. And again, we are building a rectangle inside of this. We'll draw that in red. And it's going to come down and share a side with the x-axis. All right, so for any point on this rectangle, you will notice it's going to have the ordered pair x comma y, which is actually x comma 9 minus x squared, describing that. And again, on the actual horizontal axis, the x is the width of our 1/2 of the width of our rectangle. So the full width of the rectangle, if we draw it all together, is actually 2 times x. So the area for this rectangle we know is length times width. And so for our problem, again, being a function of two variables, the area as a function of both x and y is going to be 2 times the x-coordinate times the y-coordinate. And then we know that we can replace our y with the algebraic formula y equals 9 minus x squared. So the area function as a function of x is 2 times x times 9 minus x squared. And we can simplify this down a little bit by multiplying into a polynomial form. That's going to be 18x minus 2x cubed, or negative 2x cubed plus 18 times x. And now this time around, we want to maximize this quantity. And again, we're going to follow what we've learned so far in this chapter, which is to find our derivative, find the critical numbers, and then study the sign of the derivative around those critical numbers. So we first calculate a prime, and a prime of x is equal to negative 6 times x squared plus 18. And then we'll notice that this derivative is never equal to 0. Never undefined, because it's a polynomial. It can be equal to 0 if we have negative 6x squared plus 18 equal to 0, or 6x squared equals 18, or x squared equals 3, or x equals plus or minus the square root of 3. And then just like before, we want to look at the positive values of x because we're looking at dimensions for our rectangle. So when we draw our number line for the sign of the derivative, we want to start at 0 and have our square root 3, our critical number, on that number line. Going back to our area, you will notice if we take a value that is smaller than square root of 3 but greater than 0, such as 1, it's going to be a positive derivative. And a larger value than square root of 3 would be perhaps 2. If you take 2 and substitute it into the derivative, you are going to have yourself a negative derivative. So we know that our function is increasing between 0 and square root 3, and then decreasing after that. So we do have ourselves a maximum, and it's an absolute maximum because it just decreases for the rest of the values of x, which I guess we could put on our number line as well. So our dimensions are going to be 2 times x, so it's going to be 2 square root 3, and that's going to be our width, and then our length, or in this case it's actually a height, if you will, is going to be y is equal to 9 minus the x squared, which is the square root of 3 squared. So that's just y equals 9 minus 3, better known as 6. So we have a width that is 2 square root 3 by a height or length that is 6. And then the area for such a rectangle is going to be 12 square root 3 is the area. All right, so that problem is a little shorter than the previous example, but again, the idea is that we go through and we illustrate the example best we can. So in this case, we go through and we find the largest rectangle fitting under that parabola, which opens downwards. We want to maximize the area with the constraint that the point lies on the graph of the parabola. Then we use our constraint to reduce our equation down to one variable, and then we rewrite the equation with one variable and go ahead and use calculus to find the critical numbers. We look at the number line to make sure that we have a maximum, and then we label the question or the answers with our dimensions that we found.